There is nothing better than gazing at the stars on a quiet night. But have you ever wondered how a star is formed? Thanks to the Telangana Today student edition newspaper which helped me make this script. Well, it all starts when they are born within the dust clouds which are scattered throughout most galaxies. A familiar example of such a dust cloud is the Orion Nebula. Now, what is the Orion Nebula? You see, in this example, the name is made up of two words. One is the Orion and the other is the nebula. First, we'll understand about the name Orion. The Orion Nebula is named after the constellation Orion, which is one of the most recognizable and prominent constellations in the night sky. In Greek mythology, Orion was a mighty hunter who was placed among the stars upon his death. The constellation depicts the figure of a hunter with a belt of 3 stars and a sword hanging from it. The Orion Nebula is located within the sword of the constellation Orion. Now the word nebula. A nebula is a giant gas cloud which is the first stage of 8 stages to form a star. The immense clouds of gas and dust known as a nebulae, these nebulae are composed predominantly of hydrogen and helium, the two most abundant elements in the universe. Gravity acts as the driving force, causing the regions within the nebula to condense and form denser pockets of material. Turbulence within these clouds.
My money don't jiggle jiggle, it folds. I like to see you wiggle wiggle.
Turbulence within these clouds gives rise to knots mass that the gas can begin to collapse under its own gravitational attraction. As the cloud collapses, the material at the center begins to heat up, known as a protostar, which is the second stage. Now, what is a protostar? Okay, just for explanation purposes, let's pretend that this protostar is not there. Within these dense regions called molecular clouds, the force of gravity continues to pull material together, creating a core known as a protostar. As the protostar contracts under its own gravity, it heats up, eventually reaching temperatures and pressures at which nuclear fusion reactions can occur. At this stage, the protostar is not yet generating energy through nuclear fusion, but it is steadily accumulating mass from its surrounding material. After the formation of the protostar from the nebula, the T-Tauri phase occurs. You see, in the T-Tauri phase, an enormous amount of energy is released. The average temperatures contained in the Tauri star is not enough to support the nuclear fusion at its core. In addition, T-Tauri stars denote an intermediate stage between the low-mass main sequence stage, such as a typical T-Tauri star can last for more than 100 million years. They're about 400 light years away from Earth. Okay, I think most of you didn't understand what I just said. Get this. Imagine stars like people growing up. T-Tauri stars are like teenagers, not quite grown up yet, but not babies either. They're in this special stage where they're still changing a lot. These stars hang around for super long time, like for 100 million years, and also live about 400 light years away from Earth. In the next stage, this star enters the most elaborated development stage, the main sequence phase, which is the fourth stage. When the core temperature of the protostar becomes hot enough, nuclear fusion reactions ignite, marking the beginning of the star's main sequence phase. In this stage, hydrogen atoms in case of the star fuse together to form helium, releasing vast amount of energy in the process. This energy is radiated outward, producing the light we perceive as starlight, aka what we see as stars. Yup, those are a lot of stars. So a sub to the channel would be cosmic. After the main sequence stage, the red giant or the supergiant stage occurs. You see, in this fifth stage, as a main sequence star ages and consumes all the hydrogen fuel in its core, it undergoes significant changes. In stars with low to medium masses like our Sun, the outer layers expand, causing the stars to swell in size and become a red giant. In more massive stars, expansion is even more dramatic, leading to the formation of a red supergiant. During this, the star's outer layers become more cooler, giving the stars its characteristic red hue. After this, in this sixth stage, which is the helium fusion, in the core of the red giant or the supergiant star, the temperature and pressure continues to rise, eventually reaching levels where helium fusion reactions can occur. Helium atoms fuse together to form heavier elements such as carbon and oxygen, releasing energy in the process. This stage represents a crucial transition in the beginning of the end of the star's nuclear fusion process. After this stage comes the seventh stage, which is the planetary nebula or the supernova. The fate of the star after the helium fusion depends largely on its mass. Low to medium mass stars like our Sun will shed their outer layers in a gentle, expanding shell of gas and dust known as a planetary nebula. The core that remains behind contracts to become a dense Earth-sized object known as a white dwarf. In contrast, high-mass stars undergo a supernova, during which they briefly outshine during a supernova event table. The synthesis of heavy elements such as gold, silver, and uranium, which are dispersed into space, enriching the interstellar within these elements. After this stage comes the last and final stage, where this supernova converts into a white dwarf, neutron star, or a black hole. Following the expulsion of its outer layers, the remaining core of a low to medium mass star contracts to form a white dwarf, a hot, dense object composed primarily of carbon and oxygen. White dwarfs gradually cool over billions of years, eventually fading into obscurity as they no longer generate significant amounts of energy. In more massive stars like the supernova, the core collapse continues beyond the dwarf stage, leading to the formation of neutrons, while black holes are regions of space where gravity is so strong not even light can escape. In summary, the life cycle of a star encompasses a series of dramatic transformations, from its humble beginnings as a protostar within a molecular cloud to its eventual diamonds as a white dwarf, neutron star, or a black hole. Each stage in this process shapes the evolution of galaxies and the distribution of elements throughout the cosmos, ultimately influencing the formation of new stars, planets, and even life itself.